Good evening, everyone. Welcome to tonight's distinguished lecture on the Breakthrough Prize Initiative. Before we start, I would like to thank, as we always do, our sponsors who have brought us here tonight. Of course, Technion University for having us as part of our distinguished lecture series. Thank you. And as well as all of our ISU sponsors who've made this night possible. I'd like to introduce our speaker tonight, former NASA executive and current chairman of the Breakthrough Prize Initiative, Dr. Pete Worden. Pete is known to most of us as the former director of NASA's Ames Research Center, where he led the center until his retirement in 2015. Prior to joining NASA, he held several positions in the United States Air Force and was a research professor of astronomy at the University of Arizona in Tucson. He's a recognized expert on space issues, both civil and military. Worden has authored or co-authored more than 150 scientific papers in astrophysics, space sciences, and strategic studies. He served as scientific co-investigator for 2 NASA space science missions and received the NASA Outstanding Leadership Medal in 1994 for the Clementine mission that orbited the moon. Worden announced his resignation from NASA in February of 2015, indicating he would be pursuing some long-held dreams in the private sector. And on July 20th, 2015, at the Royal Society in London, Yuri Milner, Stephen Hawking, both launched the Breakthrough Initiatives. At that press conference, Pete Worden was introduced as the chairman of the Breakthrough Prize Foundation. In this new role, Worden is tasked to run the Breakthrough Initiatives. Please help me welcome Pete Worden.
Thank you, John. And I really have to say I'm delighted to be back with ISU. I think my first interaction with ISU was 1989 or 1990 in Toronto. I was working at the White House, and these young guys, led by Peter Diamandis, came to talk to me. And Peter still looks young to me, but I don't look so young anymore. At any rate, I'm really honored to be here. To tell you a little bit about what I think is the coolest thing ever. I hope you agree. If any of you happen to be billionaires, we'd love to have your money too. But let me talk a little bit about, yes, there's a picture of me from a long ago. You know, it's funny, if you look at the official photographs of NASA senior folks, you know, you look and said, wow, NASA's really run by young people. But then you see him and you say, that was an old picture. I think that was 12 years ago, so. Where's Dave Korsmeyer? He's one of the senior NASA guys. I think he was here, he was my director of engineering. He looks older too, but that was because I was the director. At any rate, let me tell you a little bit about the Breakthrough Prize Foundation and before I launch into the initiatives. Our principal sponsor and originating sponsor is Yuri Milner, who grew up in Russia, was studying for his PhD in theoretical physics when the Cold War ended. He then decided that he wanted to do something else, so he went to Worden and got an MBA. Went back to Russia, founded one of the first big investment groups in Russia, and in the late part of the last decade, they invested in some little company in Silicon Valley, Facebook, I think it was called. They did pretty well on that. So Yuri has been a successful entrepreneur. But about the time that they invested in Facebook, he noted that when you look at list of the most admired people on the planet, and there's a lot of them around, you can look them up, that most of them don't have any scientist on them. And if they do, it's got Stephen Hawking and maybe Albert Einstein, and that's about it. His point was that over the last decade or so, there's been about $1.5 trillion made in high-tech entrepreneurship, much of it, maybe even most of it, based on scientific discoveries of the last century. And he felt we should celebrate and inspire people. So about 5 years ago, he started the Breakthrough Prize in Fundamental Physics. And the first thing that he did was figure that we ought to make it bigger than other prizes. So it's $3 million, about 3 times. There's some prize they give in Sweden. I can't remember the name. Since then, we've added 5 prizes in biological sciences. Yuri was joined by Mark Zuckerberg from Facebook, Sergey Brin from Google, and Wiki from 23andMe, and Jack Ma from Alibaba. 2 years ago, we added another prize in mathematics that Mark Zuckerberg and Yuri Milner have sponsored. But kind of the neat thing, this is the story of how I got involved in this, is that in addition to giving the prize, they wanted to do kind of a really cool ceremony. And of course, how many of you have ever, actually, I know 1 or 2 of you might, but tuned in to watch the Nobel Prize ceremony in Sweden? Probably not very many. So they decided they'd have something people might watch. So we had the people that do the Oscar party. Somebody might have heard of that. Vanity Fair, and they set up the Breakthrough Prize ceremony. It's the only black tie affair in Silicon Valley. Just to give you the idea of who we have, the last 2 years, Seth MacFarlane has emceed it. We had Christina Aguilera 2 years ago as entertainer, and Farrell this last year. So it's kind of cool people. Afterwards, if somebody buys me a drink, I'll tell you about Peter Diamandis and Christina Aguilera. It's a good story. It's worth a drink, trust me. But it's catered by the French Laundry, but they decided to hold it. If any of you have been to Silicon Valley, you drive along 101, there's these giant hangars. You know, they were from the 1930s for airships and blimps. So they held the ceremony in these hangars, Hangar 1. Now, that was on NASA Ames property, and so I was a landlord. So I signed an agreement with them. For about the 15th time, I almost got fired by the administrator for that. But we did sign it, and as the landlord, I got invited. And it's like, wow. Except I found my tux hadn't fit anymore, so I had to buy a new one. You know, it's funny how they shrink when they're in the closet. But at any rate, I got to know Yuri Milner pretty well and discovered a couple years ago he is really interested in the fundamental question of life in the universe. Where else is it? Is there intelligent life elsewhere? Maybe most important, can we go there? So a little over a year ago, he was hinting around at well, they were looking for somebody to run this, and asked me, do you know anybody that might be interested in running it? I said, well, I don't know, what do you want? He said, well, I don't know, maybe somebody that was an Air Force general at one time and maybe had something to do with some NASA center. And I said, good thing he didn't say Marines, because that was Charlie Bolden. And so I went back and told the lawyers, I said, I'm starting to talk to somebody about a new job. 1st of April last year, I came to run the initiatives. And I want to tell you about the two initial ones we've done, because I think they're really, really pretty neat. But let me have Seth MacFarlane tell you a little bit about one of them first.
This is home. But for most of our history, we knew only our cradle in the corner. We awakened on this tiny world beneath the blanket of stars, without a note to explain where we come from, who we are. We inhabited a tiny universe, oblivious to the rest of the cosmos. It was only 4 centuries ago that we began to use science to reveal nature's secrets and her laws. What is science? It's an
enough of that,
journey
right?
of discovery. It's a continuity of minds. It's standing on the shoulders of the giants who came before us, looking out
I guess this will be a short, distinguished lecture.
over a hill, up to the sky, and asking, I wonder what's there.
Oh, that view is tremendous.
It allowed us to look across space and time, see the scale of the universe, and our place in it. We now know that our galaxy alone holds hundreds of billions of stars, and that the visible universe contains at least 100 billion galaxies. In the last decade, we have discovered over 2,000 planets beyond our solar system. It's now estimated that there are tens of billions of habitable planets in our galaxy alone. Are we content to gaze at all these stars, all these worlds, from afar? We have taken to the sky. We have stepped off the Earth. We have walked on the moon. We have landed on planets and comets, and ventured to the edge of deep space. Where now?
Okay. That's all I had to say tonight. I can leave it. But I'll talk a little bit more about Breakthrough Starshot here in a bit. But I want to tell you about the other initiative that we started a little over a year ago, and that's Breakthrough Listen, which was the first major initiative. This was announced along with the initiatives at the Royal Society in London on July 20th last year, a significant date that I think everybody at ISU should know. There's Yuri Milner and Stephen Hawking. It was a really cool event. The main purpose of this event was to revitalize our search for extraterrestrial intelligence, SETI. And I'll talk a little bit about what had been going on in the past in SETI and why we're doing something new. But a lot of people ask, why are you doing this? And I thought nobody said it better than Stephen Hawking, that we are alive, we are intelligent, we must know. So when anybody asks you why we do exploration or science, I think this is the best answer. Let me start with one of the fundamental questions of science. Enrico Fermi, I think in the early 50s, formulated what's known as the Fermi Paradox. And his point was that, look, the Earth is not a terribly old planet. It's sort of middle-aged, roughly 4.5 billion years old. There are stars like the Sun that are over 10 billion years old. We assume that there's nothing unique about life, that it should exist many places in the universe. And we also assume that, that life, if it emerges many places, will ultimately evolve into intelligence of some form. And the question is that, and if it evolves to a certain level of intelligence, that it'll figure out some way to get between stars, which, by the way, we're starting to do. But the key question is, well, then where are they? They should be here. Or we should have seen some evidence of intelligence. Now, there's a lot of answers to this. And again, that's probably a question best discussed over a drink. But this is a paradox. Now, for those of you that have been to NASA Ames, we have many aliens on our staff masquerading as humans. But I couldn't get any of them to be unmasked, so I think the Fermi Paradox still stands. The problem is that when Fermi said this, nobody had done a really thorough scientific search. In the early 1960s, Frank Drake, who, by the way, is one of our senior advisors, was the first one to really start a comprehensive scientific search. He used this radio telescope at the National Radio Astronomy Observatory. His point was, look, we're starting to use radio communications. They did a calculation that said that radio communications of the power that we were using then and still are today should be detectable across hundreds, if not thousands, of light years. So he started this search. Now, by the way, we asked him if he ever had any positive signals. He said, yeah, the first time he turned it on. And he said they pointed it at two of the nearby stars like the Sun, Tau Ceti and Epsilon Eridani, immediately got signals. And he said they had the champagne open and everything, and then somebody said, well, maybe we should see what interference there might be here. And it turned out these were local radio stations, that the aliens were probably not playing Elvis Presley and so on. This has been kind of the story of SETI, that it's really a job to eliminate interference. Frank developed this very famous equation, the Drake equation, to kind of estimate how many intelligent civilizations that we may be able to detect in our galaxy. I won't go through all the terms. I mean, the number of stars that we can detect with, as I said, with sensors we have today is probably a good percentage of the ones in the galaxy. We didn't really know much about any of the rest of those parameters, but thanks to space agencies around the world, I think we now are beginning to do that. We now know, primarily due to the Kepler mission, which I had the privilege of leading Ames when that was finally developed and launched. Has shown that essentially every star has a planetary system, something we didn't know. In fact, Frank Drake said when he first started this, they were estimating maybe 1 out of 1,000 had a planetary system. So that number's gone up. We now have a reasonably good idea how many have planets in the habitable zone, and we define the habitable zone as a place where the equilibrium temperature, where the sunlight input and is re-radiated into space, is such that you would have liquid water on the surface of the planet. By the way, the first time I asked the Kepler guys to show me a chart of the habitable zone for a series of stars, they showed the sun and the Earth was outside the habitable zone. So I said, well, I'd probably need to correct that. Even a center director knows enough of that. So the Earth is now in the habitable zone. But that may be a quarter of all stars have a planet more or less the size of the Earth in the habitable zone. Of course, we don't know. There could be life developing in other places. We're looking at Europa, outer solar system objects, and so forth. So that's a pretty big number as well. Now, we don't know the rest of those numbers, but that's something we need to find out. So this is, now by the way, I point out this is sort of a very funny equation, because if any of those terms are zero, all the rest, the result is zero. But we started, as I said, October 20th last year. This is the people that were at the announcement, including Yuri Milner. I also want to, in addition to Frank Drake, point out Ann Druyan, the Cosmos creator, and Carl Sagan's widow. Carl and Frank Drake were really the people that defined in the 60s and 70s the SETI effort. I also want to point out Dario Robleto. This is a much broader idea than just science. We've included, he's a well-known artist from Texas, so this is a broad question of looking for intelligent life. Let me go back a little bit in history. There's been a lot of the notable scientists of the 19th and 20th century that thought about this. The first person that suggested, or the first group of people that suggested radio waves were Nikola Tesla, Marconi, and Edison. Indeed, I think it was Marconi that convinced the US government in the 1920s that radio could be a way to communicate between the planets and the solar system. And there was a forthcoming closest approach of Mars in quite a while. So there was the idea in 1924 that if we turned off all the radio interference, that we might be able to hear the Martians signaling us at the closest approach. So this telegraph actually went out, suggested that interfering radio antennas were turned off for a while, and we looked. Needless to say, we didn't find anything, or the Navy didn't. Unfortunately, again, until Frank Drake started his effort, there wasn't much scientific done, although we still felt the Navy knew something. Officer Lapide, you were a naval officer, weren't you? I think the space aliens were captured by the Israeli Navy. So this kind of got into the realm of science fiction for a while. But Frank Drake, as I said, brought it back, recognizing that existing radio telescopes could detect something. Now I mentioned possible detections. This is in the mid-70s. The gentleman in the center is Jerry Haman, who was a volunteer. And indeed, much of the work that has been done in this field is not by funded efforts, but by volunteers. There was a telescope, a radio telescope at Ohio State University in Columbus, Ohio, a not very good football school, says the Michigan grad. It was called the Big Ear. Unfortunately, it was torn down. There's now a golf course there. But for about 30 years, it operated looking for SETI signals. This is a very famous event. This was, I think, in 1977. This is the only, or one of the few, sort of mysterious signals that really has been well documented. Jerry Haman wrote "wow" by it, so this is the famous "wow" signal. It only existed for 30 seconds. It did not have any of the characteristics of the usual interference, although there are various people that think it was interference of some type or other. But it's never recurred, which is an interesting point. There's a whole set of books that have been written on this signal, whether it is or isn't interference. But just to say there are some unexplained signals. This is the best defined one. But when we looked at this about a year and a half ago, we found that, in fact, we haven't really looked very hard. Most of these surveys have been done either in very narrow radio frequency bands or only a very small part of the sky. So, one of the groups that say, okay, we haven't found any alien signals, that the Fermi Paradox is still a paradox, is because we haven't looked very hard in the radio. And in fact, we've looked almost not at all in the optical, where increasingly, we're using lasers to communicate. In fact, I want to put this scientist picture up. This is Jill Tarter. She's dedicated her life to looking for SETI signals. You see behind her one of the few instruments that was funded by philanthropic money. This is Paul Allen, the co-founder of Microsoft, funded the Allen Telescope Array, which Jill has used, although the array's never really been finished. One of the problems is the kind of money comes and goes. But Jill had a really interesting statement. She said, if you looked at what we've done to date, it would be like looking for fish in the ocean, dipping a glass into the ocean and looking, say there's no fish, and concluding there's no fish in the ocean. She said, well, at least we ought to use a trawler. So this is what we're trying to do, is to do a much more comprehensive survey across very broad regions of the spectrum, using modern analysis techniques that really haven't existed in the past. And the other thing it's bad for science, but it's been good for us, is that a lot of the world's largest radio and optical telescopes are no longer funded or fully funded. So we were able to get a lot of time on some of the world's biggest radio and optical telescopes. This is the Green Bank telescope. It's the largest steered antenna in the world. It's like 110 meters, I think. So that's the size of a soccer field. You really see how big it is when you go up on it. But we have 20% of the time on this. We started observing across a very broad radio spectrum, something like 2 gigahertz of bandwidth. I think it's something like from 0.8 gigahertz to like 1.8, and we're intending to expand that. This data was started around the 1st of January this year. Noting as an astronomer that you can't see all the sky from the northern hemisphere, we went to the southern hemisphere. This is the largest steered antenna in the southern hemisphere. It's the Parkes radio telescope in Australia. In fact, if any of you want one of the cutest movies ever made, it's called The Dish, a little over 10 years ago, about this telescope. This was actually the telescope that received the lunar landing signal in 1969. So it's not only historic, but pretty cool instrument. As I mentioned, we are also interested in optical SETI. This is Lick Observatory. And I want to point out that the laser beam is not from the telescope we're using. That's the Lick 120-inch. But to the left of that, you'll see two small domes. The whiter one of those two is the automated planet finder. We have 15% of the time on this telescope to look for laser signals around the nearest star. So we've just begun those observations. However, we're also interested in using new telescopes. This is the Chinese FAST telescope. We've begun discussion with the Chinese radio astronomy community. It's 500 meters in diameter. This will be the most capable radio telescope on Earth for the next decade or so. So it's one that will enable us to see deeper and more capably than we've ever done in the past. And this is this is what the square kilometer array will look like in a few years. This is in South Africa. It's a global effort. We are in discussions with the square kilometer array to use this telescope as well. The nice thing about this one is that you can steer it virtually, so we don't need to actually get time on it. We can observe what we call commensally to collect data from it. So pretty significant program. In fact, already 1 day of our Breakthrough Listen observation is equivalent to a year of previous searches. So let me tell you what we're going to look for. We're going to look at the nearest million stars. Now this number was sort of pulled out of somewhere about a year ago by some of the scientists, and I never figured out why they said 1 million stars until I started looking at this. And it turns out that if you ask yourself, well, when was the first indication that there was an industrial civilization on Earth? And so I did a lot of reading and found that most people agree that was about 2,000 years ago. The Romans cut down most of the forest in what's now Spain to smelt silver. And they made changes by that smelting to the atmosphere that are, you can see the evidence of that in the Greenland ice sheets and Antarctic ice sheets. So this was a pollutant that could have been detected 2,000 years ago. But if you now figure, well, all right, the signal went out, an alien civilization was watching the Earth and suddenly saw a spike in indication of industry and then decided to signal us back. So the signal had to go out 1,000 years, and then they signaled us back. So 2,000 years ago, there are 1 million stars within 1,000 light years. So this is a pretty, thorough survey we're going to do, and it's I think it's something like 0.1% of the galaxy's stars. So we'll begin, if we don't see anything, set at least a lower limit on some of those other parameters, at least in terms of civilizations trying to signal us. We're going to scan through the center of the galaxy, where we'll get at a good percentage of the stars in the galaxy. Something like 30 or 40% of the stars in the galaxy are in the direction of the galactic center. Most of the rest are in the plane of the galaxy, so we'll scan through the Milky Way plane. And in case there are incredibly advanced civilizations in other galaxies nearby, we'll be looking at them, the 100 nearest galaxies. Those of you that are familiar with this field know these are the Kardashev level 3 civilizations, so if one of those exists nearby, we hope to find it. Another key part of what we're doing is trying to make as much of the data as we can available to the public. There already exists a substantial public effort called SETI at Home. We are working with the University of California at Berkeley to lead Breakthrough Listen. They also lead the SETI at Home effort. How many of you have downloaded the SETI at Home saver? Good. The rest of you need to help us too. This is some 6 million people around the world have downloaded the screensaver. The combined computer power is roughly comparable to, some of the world's largest supercomputers. I think it's still bigger than the Pleiades computer at NASA Ames, so we're going to keep ahead of them. This, by the way, every year gives a few dozen detections that need to be followed up that are anomalous. And one of the things we're going to be doing is following up with these other telescopes on those detections. But this is another effort. We will soon begin to, we've already made some data available, but we'll soon make a lot more data available for the public to look at. I might mention that one of the most interesting suggestions of how to look at the data we get came from a very unlikely source. I think most of you know who Edward Snowden is. Mr. Snowden had an interview through some mysterious means with Neil deGrasse Tyson. I think it was last September, shortly after we announced our initiative, and I'm sure the NSA wants to know how Neil deGrasse Tyson got that. Anyhow, Tyson asked him if he'd heard of the Breakthrough Listen effort, and he said yes. And he asked him what he thought about it, and he said, "Well, you should look for encrypted signals." And we hadn't really thought about that. I suppose Edward would. But indeed, he's correct. In fact, most signals that are not particularly intended for somebody are encrypted to minimize noise, and they're now spread spectrum and so on. So one of the things we do, we want to make data available, so if Edward Snowden can download it, maybe he'll find our answer. And a lot of people like him. Now, if there's somebody from the NSA, we might not hear about it, but at least they'll have processed the data. Now let me turn to Breakthrough Starshot, which was mentioned in the beginning. One of the key things that Yuri Milner said to me was, what if we find even a life-bearing planet or one of the nearest stars, can we go there? The answer was kind of no until recently. There's been a number of primarily NASA studies in the NASA Innovative and Advanced Concepts program, which I think is one of the coolest things anybody does in the government. We started about a year ago looking at NASA and other studies about how to do interstellar flight. We constituted a review group that was headed by Professor Avi Loeb, an Israeli, by the way. Professor Loeb was also he was a Talpiot grad, I think. SETI has a group called the Center for Theory and Computation at Harvard, and we would send ideas to him, and he would usually call back and politely say it was rubbish. But one he didn't. About 2 or 3 years ago, the NASA, or the NIAC they call it, funded an effort by Professor Phil Lubin at University of California at Santa Barbara that suggested we look at a concept that really came out in the early 60s, that we use laser-driven light sails. We use photon pressure. I'll talk to you a little more about that. But that concept looked possible, and so we decided after several months of analysis that it was reasonable enough. So at 12th of April 2016, Yuri's night. Yuri Milner, by the way, is named after him. His mother confirmed that to us, so we know it's true. But we made an announcement at the One World Observatory in New York that we got Professor Hawking there as well, and Hawking, Milner, and this other kid here agreed to be our board. We have some pretty distinguished board members, and you can see in the upper right there some of the key leaders in that. The person on the right is Professor Lubin, and then Professor Loeb. Then there's some old guy there, I don't know why they put him there. And Mae Jemison, former astronaut and the head of the 100-Year Starship Foundation. So and then Yuri Milner and Hawking, of course. I mentioned Yuri Gagarin. As I said, in addition to Yuri being named after him, this was the first, I think, space, breakthrough that was made by humanity. Of course, the next one was a little over a decade later, or less than a decade, was the Lunar Landing. So we are hoping that these aren't the last breakthroughs, and that's what we're really aiming for. Now this is Voyager, that it's shown in our initial video. It's at the edge of interstellar space, I think about 130 astronomical units. The astronomical unit is the distance between the Earth and the Sun. And it's close to one of the fastest things that humanity's ever produced. However, if you want to go to the nearby star, or the nearest star, even if that was aimed in the right direction, it would take something like 80,000 years. So probably none of us will be around to see the results. So we need to go a little faster. Now, just to kind of go through, why do we think that there's something interesting around the nearby stars? As I said, this is the Kepler data that, again, to repeat, showed that we think at least a quarter of the nearby stars could have a habitable zone planet the size of the Earth. Now, this is people in the southern hemisphere will probably know this better, but how many of you know what these two stars are? This is Alpha and Beta Centauri. The one on the left is Alpha Centauri. That's the nearest star system. There's actually 3 stars in the system. Alpha Centauri itself, which is the brightest star in the southern hemisphere, that's not visible from the north, is 2 stars, and I'll talk a little bit more about them in a minute. But there's a 3rd star in the system called Proxima Centauri, which is a small star. The 2 primary stars, Alpha Centauri A and B, are pretty much like the Sun. Alpha Centauri A is a little bigger. Alpha Centauri B is a little smaller. But Proxima Centauri is pretty far away. In fact, there's even an argument if it's attached to Alpha Centauri A or B, and it's actually closer to the Sun by a bit. But it's a red dwarf star. It's a little small star. So we're intending to look at all 3 of these stars. We're about to begin a program to look at Alpha Centauri A and B to see if there are habitable zone planets, and there are other ongoing things on Proxima Centauri. Now, there's another reason to look at these stars. How many of you know what this is? Come on now, some of you are geeks. I've seen some of you walk around on the campus with your cell phone. This is Mew and Mewtwo, and they're the rarest and never seen Pokemon. And I'll tell you a little secret, they're actually in the Alpha Centauri system, so that's another reason to go there. I've got a couple of my associates who got me addicted to this a week ago, so they're responsible. But this is far away. I did give you most of you probably know at ISU what this is. But the reason I put the moon up here is to give you an idea how far away Alpha Centauri is if if you said, well, let's collapse the scale and say, the moon is really about, if it was there where you're sitting, that's the basic scale. Alpha Centauri would be where the moon really is. So it's a long way away, some 300,000 times further away from the Sun. To get there in a reasonable amount of time, we need to go something like 1,000 times faster than we can today, probably 20% the speed of light. So this was the question: how do you get to these speeds? Now, just on a kind of civilization scale, that in the first 100 years of technology, we increased the speed that we could go by a factor of 1,000. So we just need to continue that just another 50 years or so, and we'll be there, right? Of course, the first thing you'd look is how about chemical rockets? And you can do a calculation using the rocket equation. even I could do a calculation doing the rocket equation. And you find out that, yeah, you can build a rocket that would take you to 20% light speed, but the amount of fuel it would need would be roughly the mass of the galaxy, even beyond NASA's budget. Now, there's been a lot of people who have talked about fusion and fission. In fact, you can do a calculation that says that if you build a fusion rocket that's, not much bigger than current rockets today, you could probably send something to 10 or 20% light speed. The trouble is that fusion energy, as it's been said, is the energy of the future, always has been and always will be. So that nobody knows how to make this work. And I will tell you that the first set of things we had Professor Loeb look at was fusion and fission. In fact, I think I talked to a couple folks here about antimatter-driven fission systems, and they just, you've got a little problem of, well, the fusion doesn't work, and if you want to use antimatter, you need a lot of it, and we can produce it like 20 atoms a year, so we've got a ways to go on that one. So we decided to go to an old technology where you say, well, let's keep the fuel at home and just use what we find. So this is a sailboat, for those of you that haven't been to school recently. So this is a concept actually is really old, and to use it for space sailing, we actually, this is the first reference we could find. So this is a pretty credible one that Kepler wrote to Galileo in 1610, talking about sailing on heavenly winds. Now, we're not sure what he was talking about, but maybe now we know that using light pressure on a sail to push things. And this is, a new technology, but it works. This is the Icarus probe of a few years ago that demonstrated that solar sailing really does work. The trouble is that sunlight is really weak. And if you do a calculation, say I want to use sunlight to push something, you might be able to get it to hundreds, maybe even 1,000 kilometers a second, but we're still kind of like 2 orders of magnitude short of where we need to be to go interstellar distances. Fortunately, there's been a couple advances. The first one is in microelectronics, that we can make things smaller and smaller. The second one is in photonics, largely driven by the internet, that we can gang lasers together and begin to get very, very powerful lasers. And just to give you kind of a scale, this is a satellite today. Sending this interstellar distances would be impossible without lasers that we couldn't even imagine. However, point out that we can do a lot with electronics. We can make things that are really small, and so we've decided to look at what I'll call a star chip. In fact, I have one with me. This is about the size of something we think we could send interstellar distances. This is a mock-up of a completely functioning satellite that we could send at maybe 20% light speed. And this technology is actually pretty much here today. It's about the size of the chip in an Apple Watch. We've gone through, and even today you can find these components that cameras, batteries made with radioisotopes, lasers for communicating, processors and cameras and so forth. This exists, or soon will. So this was constructed for us by Mason Peck, the former chief technologist at NASA. In fact, we can go through and say, what's the mass of these things that exist today, and it's about 1/3 of a gram. Now, so sending something that can do things deep into space looks like a reasonable technology. But the other key technology there is getting enough laser power and building a sail. And I'll tell you that the basic model we have is a sail about 4 meters in diameter, and the amount of laser power one needs is a mere 50 gigawatts. So one of our challenges is how do you put that much power on a sail that's maybe a few hundred molecules thick without it tearing apart? There are experts that say we can do it, but that is a big challenge. I mentioned lasers. We can probably put together a 50 gigawatt laser today, but it would cost something like, trillions of dollars. So even Mark Zuckerberg probably wouldn't fund that. But we think the price is going down on lasers. Indeed, we're finding there's a Moore's law for the cost of lasers. So something like, a factor of 2 every year or 2. Also, the power of lasers is going up. And we look at this and we believe that you could build a 50 gigawatt laser that's about a kilometer square. This is about the size of the square kilometer radio telescope that's being built today. So we think within a decade or 2, it's feasible to build a laser that's powerful enough. Now, any of you that go through this say that, look, like this is really hard. There's a lot of things other than, as I mentioned, you've actually got to prove that you can build a star chip. The sail is a big, big problem. This much power, being able to get it through the Earth's atmosphere and pushing something. Of course, the cost of the laser is significant. And by the way, and I know there's some policy people here, there's a big policy issue. We're going to build a humongous laser, and that's a scientific term, somewhere on the planet and fire 50 gigawatts into space. There's going to be people who say, well, what if it hits my satellite? So we got to figure that out. And so that's one minor policy issue. We've got to be able to launch these things and aim them at the right planet. So that, by the way, they can maneuver a little bit. There's little small lasers on board that can push it a little bit, not very much, using photon propulsion. Cruising for 20 years in interstellar space, there's like, some of the astronomers would say there's like junk there. There is, dust, gas. In fact, our calculations show that this chip may hit, a few dozen small pieces of dust. We think it can be shielded, but that's a big issue. Then pointing the thing after you get it there and communicating back to Earth so we can determine what it found. It flies right through the other star system in a few hours. It's kind of comparable to flyby of Pluto, and then communicating the data back. There's about 25 of these challenges. We put them on our website. We've asked experts around the world to look at them, and we've gotten some answers. We think this is feasible. Yuri Milner committed the first $100 million for this. We've constituted an advisory panel that will meet for the first time in about 2 weeks in California. We've managed to inspire and get a number of some of the world's brightest people to help us with this on our advisory committee. People like Stephen Chu, Nobel laureate, some of the other people that have done some of the most impressive work on lasers and so forth. So we think we're at least harnessing the world's experts. So as I mentioned, $100 million is the first phase. We hope to solve the two biggest problems, which are affordably constructing the laser, getting the light through the atmosphere, and keeping the sail together. A lot of you'd say, well, 100 million is not going to get you an interstellar system. We know that. But we think if we solve those, Mr. Milner and his colleagues seem willing to raise about $1 billion to build a prototype. We'll spend about 5, 6, 7 years on the first phase. And then we'd like to raise about $1 billion to do a prototype to see if we can send something like this in space at as close as we get to 1% light speed. If that works, we believe then that we can probably raise the money as a public-private partnership with governments around the world, so that within a generation that we can launch humanity's first interstellar mission to Alpha Centauri. This, of course, is hard, but one of the folks we talked to about this was Kip Thorne, who was involved in the gravitational wave detection. He said, look, your challenges are about the same as they found theirs were 40, 50 years ago when they started gravitational wave detection. In fact, Albert Einstein, soon after he predicted gravitational waves, said, they asked him, do you think they'll ever be detected? He says, no, never. So we think this is certainly a reasonable possibility. We are inviting the world to participate. We're going to publish everything openly. This is not a classified or sensitive thing. Well, it's sensitive, but we want everybody involved in it. But let me spend a minute to tell you how we think it works. So we have this kilometer array, and this is just an artist's conception. We have a mothership that has hundreds of these star chips. We're not going to send just one. It will deploy them. Then the move out of the way, of course, because there's a lot of power. Pretty cool. You move all the... and then you fire the lasers, which are like humongous. Push this thing for about 2 minutes. Accelerates at a mere 60,000 Gs. People ask, will there be astronauts riding on board? Probably not. It soon gets out of range. It goes from about 50,000 kilometers to 2 million kilometers in the 2 minutes, and then off towards Alpha Centauri. It flies edge on to minimize the cross-sectional hits with interstellar dust for 20 years. Then flies by the Alpha Centauri system. It's able to change its orientation, so when it flies by the planets that we hope to find there, it will take some images. Here's the images. And then, of course, you got to get the data back to Earth, and this is where another magic thing happens. It reshapes the sail to transmit, because there's a small laser on board, the beam back to Earth, which is detected by the 4.5 years later by the transmitting array. We have to use it as a receiver as well. So there's a few challenges there to produce, but we think we have a start. A really cool effort, and we want you all to help us. So one reason I'm here is to solicit support. As I said, the challenges are not just scientific and technical, they're also political and so forth. I will stop there, but before I finish, I want to echo John's thank you for the sponsors of this ISU session. It's the same sponsors we're going to try to hit up too, so be nice to them. And there will be future events, so I'll put up this from our main sponsor. And I'll thank you for your attention and look forward to working with all of you in the decades ahead. Thank you. And I think we have time for a few questions. By the way, some of our challenges came from these question and answer things, so I got a couple of guys up here to write them down. Yes?
Yeah, I wanted to ask, at 20% the speed of light, what if it hits something?
Well, to use another technical term, that sucks. We will hit dust in interstellar space. That starship will have to be shielded, probably with a little bit of tungsten. If it hits the sail, it just goes through it, doesn't do much damage. That's one of the reasons we're going to send hundreds and not just...
Hitting a planet, for example.
Well, that would be a surprise. Hopefully we know where the planets are. In fact, we will know where the planets are. I think we're going to know very soon. I believe in the next 5 years, we're going to fund some efforts. There are others that are ongoing. So we're not, we've got enough maneuver. We will miss the planet by quite a bit, like maybe half an astronomical unit. Now, if you did hit the planet, there's a lot of energy in these. It's like 400 or 500 tons of TNT equivalent. But that's about what the Earth gets hit 4 or 5 times a year by asteroids about that size. It would detonate in the upper atmosphere. If it was a civilization like ours, it would look, much like being hit by an asteroid, a small one. If it's bare rock, it'll make a small crater. But one of the things I think, by the time we launch these things, we'll have studied pretty carefully the Alpha Centauri system and be pretty confident that there's not some civilization there is going to say, hey, those creeps are shooting at us. Let's shoot back. So I mean, but that is a policy issue. And so it's not completely trivial, but we don't think it's going to be a showstopper. But it's a good question. We did the calculation, that's why we knew. Next question? Yeah.
Thank you very much. I was just wondering, in relation to 50 gigawatts going into a probe of that size, what areas of research need to be done in terms of potential reflectiveness or nanotechnology to basically make sure it doesn't melt or...
Well, quite a lot, actually. But we've gone through the calculations. There are materials today, although they probably weigh, hundreds of grams for a sail that size. We've looked at dielectrics. The reflectivity doesn't have to be that high, 80, 90%. The key thing, though, is the absorptivity needs to be about 10 to the minus 5. And there are materials today. Now, laser light is monochromatic, so you can probably do better at that. However, as I'm sure some of you are calculating, say, well, no, wait a minute. He's accelerating this thing in a couple minutes, so there's a redshift. We start with probably 1 micron diode lasers is most likely today. And then by the time it finishes, that it's going to look like 1.2 microns. So we're looking at, can you tune the laser and keep it at the wavelength you need to, or can you build broader, low absorptivity efforts? One of the key things we're doing is assembling a global panel of the best materials people. In my mind, this is probably the hardest challenge, is the sail. So that's the one we're going to put the most effort up front. It's again, when the people that we've talked to today say, yeah, it's doable. In fact, it's a really cool challenge. Can we work on it? So as long as they say that, yes. Now, of course, they're happy if we write checks, but we got to check on the calculations. But our initial work, we said, yeah, it can be done.
Okay. Is this working now? Great.
Yeah.
So I think it's clear that all of us would like to know if there's life in the universe. The other question I would ask is, do we want them to know that we're here, or have we already been broadcasting to them? And is there a policy on this type of issue from the United States or other countries or privately?
That's an excellent question. In fact, we had another initiative we announced called Breakthrough Message. And we still intend to do this. Will be a $1 million contest globally to figure out what would you say if we found a signal. But we had to say very emphatically, we're not going to send anything. This is actually quite a interesting debate. Hawking himself thinks it's a bad idea to message. If you look at human history, if less technically advanced civilizations signal more technically advanced civilizations and draw attention to themselves, it usually doesn't end well. There's a lot of different arguments on that. They say, well, if it was an advanced civilization, they would all be peace-loving and wonderful. Your guess is as good as mine. On the other side, or on one of the other arguments is that assuming, and everything indicates this is correct, that you can't fly faster than the speed of light or get any place faster than the speed of light, it's likely that the nearest civilization is probably a long ways away, hundreds or thousands of light years. It would be a long time even to communicate with them. The dialogue would be, human history time scales, not short. But nonetheless, that is a very legitimate question. We believe that needs to be discussed in a global forum, probably using the UN or others. And one of the things we are interested in the future is sponsoring such fora. We have begun a series of what we call breakthrough discuss conferences that are beginning to look at the questions of not just flying to the nearest star, but communications and some of the policy issues about that. But I think it's a very legitimate question. Now, the other part of it is that well, maybe they've already, it's too late. We have transmitted "I love Lucy" and Mr. Trump speeches and everything else. See, it's good not working for the government. I don't care what. I can tell you something nasty about the other candidate too. If you do the calculation, and you say that if it's a leakage, that if it's an unintentional signal, it's hard to see it very far. In fact, just now do we have enough sensitivity in these programs I talked about to actually see "I love Lucy" or a Trump speech or a Hillary speech or anything else from even the nearest star. I mean, we can probably see out to 10 light years or so, that kind of transmission. Now, obviously, say if they have more advanced technology, they can probably do better. On the other hand, a directed signal, say if we took the Arecibo radio telescope, the 300-meter telescope, with the megawatt transmitter it has out today, you can calculate that it would be seen a good fraction of the distance to the center of the galaxy, thousands of light years. So there's a real difference between just listening for random, unintentional signals and actually listening for a signal transmit. So I think that's one of the things that one needs to consider as well, just listening for unintentional signals or sending out unintentional signals and one deliberately sent needs more policy discussion. Well, actually, there has been efforts. In fact, the first effort that I know of was by Sagan and Drake. Drake now thinks it's a bad idea. But they sent out the famous Arecibo message. I think it was to a globular cluster like 25,000 light years away. So we haven't got an answer yet. Probably, shouldn't really wait for one. But there have been a couple other efforts, maybe a dozen or so. Most of them, in fact, I understood that in the 60s, the Russians sent out the collected works of Lenin or something. So, I mean, there's been a few efforts like that. I think people have sent out, musicians' works. So, the aliens might say, "What god-awful noise." But at any rate, there hasn't really been, I think, a powerful, well-organized effort. And I don't think there should be until it's been discussed thoroughly and we get an idea. And I think people should think about what they would send. I think that's something we ought to begin right away. Yeah,
so you had kind of a call to action for everybody to get involved.
Yep.
I see this name with Nobel Prize winners and a lot of really amazing people. I was wondering if you could comment on exactly what it is that you'd like all of us to do, and if it's mostly outreach and raising awareness, or if there's actually a way to get involved with problem solving.
All the above. We have if you look at the Breakthrough Initiatives website, we've listed these 26 or so challenges. We're soliciting inputs from that. We have asked about 100 of the world's scientists. We're also asking people there to give us their idea of what we can solve. We are in the process of setting up a much more flexible online forum that we're going to have members of our advisory committee moderate that. I would expect probably by the end of the year that will be live. So it's so the idea is not just that you put your idea out there, but somebody will be able to respond to it and say, hey, look, we thought about that, or no, that's a really cool one. Also by the end of this year, and in part based on those inputs, we'll start figuring out what availability for funds and so forth. So the answer is absolutely to start getting those responses. One of the problems is, well, it's not a problem so much. In fact, it's cool in one sense, is our staff is pretty small. In fact, 3/4 of the staff is here. And to try to get that set up, we're really enlisting a lot of the world's best scientists to help us with this. As I said, they will be moderating those discussions. So stay tuned. Yeah, join us. Yeah. James Skulkfake, who's our research associate, said he promised he'll buy drinks for anybody that show up. So.
Hi. First of all, I wanted to thank you because 2 years ago, thanks for your management, I could go to NASA to do an internship. So thanks for that. And my question is, or maybe it's a proposal. As you may know, here in SSP, we work as a team projects.
Yep.
So maybe for SSP17, SSP can work this idea for a team project. I don't know, maybe the organization can be interested to have 100 people working on this in summer, so maybe it can work.
That's an outstanding idea, and I'm going to push my sponsors to say, they had to come and talk to you folks, because you're the people that are going to make this work. I probably
that would be awesome.
I probably won't be alive when it flies by Alpha Centauri, but I think you will, especially if I take James up on his drinks tonight.
Please, James.
Yeah. Let's see, who's...
Hi, I have a technical question. Why do you plan to accelerate using the lasers for only 2 minutes? Is there a reason why you cannot track for longer and use less power?
We have a model that you calculate. You've got a number of variables. One of those is the size of the sail, but then also as the sail size goes up, the mass goes up. You could use a lower power laser to accelerate longer, but it turns out the end velocity is less. We were at kind of the peak there. One of the problems as you start to accelerate it, it goes out of range pretty fast. And what you're doing is focusing this array laser on a spot. And you need to optimize the size of the array, the power in it, with the size of your sail. You start pushing it, and if it accelerates at tens of thousands of Gs, it's out of range pretty fast. If you accelerate slower, it still gets out of range pretty fast, but the peak of that effectiveness looks to be at around a few meters, a gram, and sort of tens of gigawatts in an array that's a kilometer. We did a lot of variables, said what about 2 kilometers? Then you start to really drive up the cost of the array. You look at a bigger sail and you start running the mass up. It turns out that there are some other really interesting things you can do with this array. If you use a bigger sail and accelerate it more slowly, you can put a lot bigger payload. You're not going to go to these fractions of light speed, but you can go around the entire solar system pretty well. You can put 100 kilograms at maybe 1,000 kilometers a second. So that's kind of interesting. You get out to Pluto in a few months rather than decades. So I think this is a really interesting area of optimizing the array. So one of the key, I will say the third challenge we have is to build a systems model that allows us to do those excursions a lot more than a rather simple model. But right today, that was the sweet spot in our analysis. And it's way up in the corner, and it's just feasible. When we looked at other things, they looked less feasible.
So there are a lot of examples in astrophysics of scientists planning a project and then other scientists doing cool science with it, which was not planned, like science with the calibration trash of HST or stuff like that. So I was wondering, regarding your first project, the radio, have you been approached by radio astronomers who want to use your data for other purposes?
Absolutely. In fact, we have an advisory team for the Breakthrough Listen that consists of some of the world's best radio astronomers, people like Ron Icarus in Australia, that really sort of the greats of radio astronomy. This is going to collect an incredible data set. One of the things we're planning to do is to scan, at least once a year, the entire plane of the galaxy and make that data all available online. We're planning on making the raw voltages available. so that a lot of the problem is when you try to store that much data, people tend to throw stuff away. We'd like to do it so we don't throw anything away. That will be an incredible database of sort of a digital radio sky survey of at least the plane of the galaxy, so that we'll be able to detect a lot of pulsars and other objects. So we're expecting some pretty cool data sets, but perfect point. By the way, on the Starshot program, this will be a kilometer telescope, so it'll be able to do some pretty cool stuff for astronomy as well.
Hi, I really like the Starshot idea, but I have a question. If these chips are traveling at 0.2 the speed of light and reaching these other solar systems at that speed as well, when they pass planets, wouldn't any image that they take be a blur? Or how do they?
Yes, but those are, we've done the calculations on that. You're able to, it depends how you clock the detectors. So you can clock them fast enough to, as the planet moves, the blur will be de-blurred. But it's that is a challenge, not an insurmountable one in the software and the chip design. But yes, it's certainly a consideration to. We also don't intend to fly that close to the planet, so we'll be maybe a half an astronomical unit. So, I mean, you're going by fast, but it's not, that fast. I mean, to travel an astronomical unit at 2/10 light speed is, something like, an hour and a half, 40 minutes, if I got the calculations right. So, you get enough time to get and you can use the small pointing lasers on board to cause the sail to rotate at the right speed.
Have you considered generating the laser pulse from orbit to eliminate all those atmosphere ionization and policy issues?
And a matter of fact, we did. The initial paper by Phil Lubin talks about a space laser system. He talked about a 10 kilometer by 10 kilometer array. The problem is when you look at the cost of that, at least today, that's not feasible. There is a policy problem that's probably worse. If you put this thing in the ground, it can't hit the planet. But you put it in space, and remember I said this is, equivalent of hundreds of tons of TNT. There's always an argument, what if some bad people turn it around and shoot at something? Well, that's fine if you could put it far enough out, but then it becomes even more expensive. Now, it may turn out that in a few decades that our space manufacturing capability is good enough that you would put it, someplace deep in space or on the far side of the moon. So that's certainly an excursion that, indeed, like I said, if you ask Phil Lubin, he thinks that's a better idea. But we think that, at least with the current level of technology and anticipated level of technology, putting it on Earth will be cheaper. By the way, the most likely place for it is you want a very high altitude, dry location, plus noting that Alpha Centauri is minus 60 some degrees. It has to be in the southern hemisphere. The absolute best location is the Atacama Desert in Chile. The Chilean government has asked to talk to us positively, but we certainly need to do that soon. The other alternative is that has some of those characteristics is Dome C in Antarctica, but the cost of putting things in Antarctica is probably an order of magnitude higher. So, but those are certainly trades we need to do. The first real decision is the prototype, which is probably a 50 meter to 100 meter transmitter, probably in the 100 megawatt range. So that's, we will decide there where the best place to put it, but probably the Atacama Desert in Chile is the ideal location. Yes, because what you do is you don't need 50 gigawatts. We're only going to fire it once a day. You need to store the power, however. So we figure a couple hundred megawatt, which is a sort of modest size, doable power plant. Then you store it. Now the storage is hard. We've looked at 3 different approaches. One is using capacitor banks. The second one is using flywheels. The third one are batteries. All of those are feasible, but that's a major cost driver. But 250 megawatts is about a kind of a medium-sized power plant. It does turn out there is not far from the Atacama Desert is a natural gas pipeline that could power such a plant. We've also looked at could you put a solar plant there? That's another possibility. So these are all things we'd have to do, but it is not an absurd level of power. It's about 1.5 to 2 gigawatt hours of power equivalent. That's something that we think we can store.
Okay. Pete, we'll take one more question here, if that's okay.
Yep.
I'm an SSP student from China, and I'm very glad to hear the details from you. I'd like to say that Steve Hawking posted his first Weibo, the Chinese Twitter, on 13 April this year. And since it's his first Weibo, it has drawn dramatic attention on the Chinese internet. And I read the newspaper, he announced the breakthrough Starshot, and it's the first time I know about the program. So I'm very glad today to hear more details about you. And my question is, since you've used the laser technique and you said that it's growing very fast, so do you think it is possible that we use the laser beam to remove the space debris, just like you did?
Yes, exactly. In fact, that's one of the other uses of potentially a powerful laser. Indeed, I think you wouldn't need that much power. Another application that we haven't calculated, but if there's an asteroid that looks like it's going to hit the Earth, that you can push it. It doesn't have to be pushed very much. So there's a lot of other applications to this. I might also add that we've begun discussions with some experts in China about putting a northern hemisphere array in the plateau in Tibet. So there's, if you wanted to go to the next nearest star after Alpha Centauri, it's Barnard Star, which is accessible from the northern hemisphere. So there's I think, a lot of potential interest in having a couple of these arrays. They have a lot of other good purposes. Of course, I think again, whatever we do globally would be a public-private partnership subject to global policy constraints. But yes, exactly. Absolutely, and in fact, some of the discussions that we've had are experts here in Israel about some of these technologies.
All right, thank you. Let's give Pete a big round of thanks. I wanted to save the best for last. Pete is also a member of the ISU Board of Trustees, so he is one of you. Okay, before we break, I'd like to remind you of some other public events coming up here in Churchill Auditorium. In 2 days, on Thursday, we have our Arthur C. Clarke panel, Where Space Meets Popular Culture. And then coming up in 2 weeks, distinguished astronomer David Levy will be here talking about a night watchman's journey on Monday, August 15th. So again, thank you all for attending tonight. Let's give ourselves a big hand, and thank you again to Dr. Pete Worden. And we'll see you all back here in 2 days. Thank you.